So in this lecture, this will be our first lecture over chapter 8, which looks at the reactions of alkenes. So in the last chapter, we looked at reactions that make alkenes, and in this chapter, we'll look at several reactions that alkenes undergo, mainly what are known as addition reactions and oxidation reactions. So we'll look at about 15 to 20 different reactions in this chapter. Some of them are similar, but they're different reagents. So that's the first example. If we take an alkene and react it with H2 and palladium. So palladium is serving as a metal catalyst in this reaction. If you remember what a catalyst is, it's something that speeds up a reaction. And it could be a variety of different metal catalysts that work. It could be platinum, could be palladium, could be nickel, could be rhodium, for example. And these reactions usually work at room temperature. So basically what happens in the reaction is, so H2 just provides two hydrogen atoms, and you basically just add hydrogen and hydrogen across the double bond. So you take an alkene and you make an alkane out of it by adding hydrogen and hydrogen across the double bond. So the metal catalysts are usually insoluble, and so you're doing what's known as heterogeneous catalysis. So that means the reaction's occurring in at least two different phases. So in this case, it's a solid phase because the platinum or palladium doesn't dissolve. And then the alkene could be introduced as a gas, or it could be in a solution. So then you have two different phases that way. So basically the way the reaction works, so again, you have your palladium surface, so palladium atoms, and then hydrogen's a gas, so hydrogen absorbs onto the surface of the palladium. So that's what this would indicate then. So the hydrogen is now absorbed onto the surface of the palladium. And the palladium is basically, one thing it's going to do is weaken the hydrogen-hydrogen bond. So that's going to make the hydrogen more reactive. And then for your alkene, so if you remember, if you have a carbon-carbon double bond, then that means each carbon's got a p orbital on it with one electron in it. And so the alkene then is going to float in over the surface of the palladium, which has got the two hydrogens on it, and it's going to basically pick up two hydrogens from the surface of the palladium. And so because of that, since both hydrogens are adding at the same time, and the alkene is just coming across the surface and picking up those two hydrogens, the two hydrogens are going to add to the same face of the alkene. So you're going to do what's known as a syn addition, or the two hydrogens are adding to the same side, so they're adding cis with respect to each other. Okay, so again, what does a catalyst do? So this is an energy profile for the reaction. So as the reaction proceeds, would be what's on the horizontal axis, and then on the vertical axis is energy. So the line drawn would be, for example, the energy without a catalyst. And if you remember from General Chemistry 2, the rate of that reaction depends on the activation energy, the energy between the starting material and the transition state. And so what does a catalyst do? Is it basically lowers the energy of that activation. So that would be the energy of activation with the catalyst. So the activation energy is lower. So, and it can change the entire course of the reaction, but you start and you end at the same spot. But overall, it has a lower activation energy, so the rate is faster. Okay, so but basically what you're going to have to be able to do in this class is just predict the product. So if you have an alkene and you see H2 and a metal catalyst, just add H and H across the double bond, cis to each other. So you would end up with, so those two hydrogens could add to the top or they could add to the bottom. All right, so that would be if you added them to the bottom or if you added them to the top. All right, then that's what the product would look like. But in this case, it doesn't matter because those two molecules are the same, right? Why are those two molecules the same? Because this has an internal plane of symmetry with two chiral carbons. So this is a meso compound, which means it's a mirror image. So if you change both chiral centers, right, because we switched the methyl and the hydrogen, then that would create its mirror image, which would normally be the enantiomer, except for the fact that this is a meso compound, which means these two molecules are the same. But the point is, you had to clearly show the stereochemistry in the reaction since it's an addition. So if you were given this problem and you just gave that as the answer, right? So basically, you get to get rid of the double bond and add hydrogen and hydrogen. So if you just show that, then you've recognized that hydrogen adds to the double bond, but you didn't indicate that they're cis to each other. So you missed part of the problem. Okay, so just as a couple more examples. So if we took this alkene and we want to clearly illustrate that it's cis or syn addition, then rather than looking at the molecule from this perspective, let's draw it from that perspective. So rather, if drawn like this, then all of the atoms are in the plane, and if we draw it like that, then the ethyl group would be coming towards you, and the methyl group coming towards you, and the CH3 going away, and the CH2, CH3 going away. And so now if you want to illustrate the hydrogens add syn to each other, then you could do it like that. And now again, in this case, we've made it two chiral carbons, right? And is this a meso compound? And the answer is no. So the way it's drawn right now, the hydrogens reflect to each other, but the methyl and ethyls don't reflect to each other. So that's not a meso compound. So this would technically create two stereoisomers. And if you wanted to illustrate those two stereoisomers, then you could do it like that. So the hydrogens could add, if it's drawn from this perspective, the hydrogens could add from the bottom, or they could add from the top, and that creates a pair of enantiomers in this case. Or if this was our molecule, and again, if we draw it from a side perspective, where the two methyls are back and the two ethyls are front, then if the hydrogens add to each other, syn to each other, so if we had that versus that, so those are both syn additions, but these two molecules are the same, right? Because this molecule has an internal plane of symmetry, so it's meso. So this is the same as that. Okay, so that's one reaction of the 15 to 20 in this chapter. So next reaction. So if we take an alkene and react it with HX, so X being halogen, so it could be HCl or HBr. So one thing to recognize, so since you have a double bond, then you have a pi system with electrons in it, and that is electron rich. So alkenes can act as nucleophiles in reactions. And so if you react it with HX, well, H is partial positive and chlorine is partial negative. So H is would be electrophilic. So if you have an alkene that's a nucleophile, it's going to react with the electrophile first. Since this is electron rich, the alkene, and the H is electron poor, then that's what's going to happen in the first part of the reaction, is the alkene is going to react with the hydrogen. So we're going to take the two electrons in the double bond, and we're going to use them to make a bond to hydrogen. So you could add hydrogen to either carbon. So if we call this carbon 1, 2, and 3, so you could add the hydrogen to carbon 1, which would look like this. So now we added the hydrogen there, so now the carbon in the middle is electron deficient, so that would be a carbocation. or we could add the hydrogen to carbon 2. And then the first carbon would be electron deficient. So you make a carbocation in this reaction. And so which of those two carbocations is more stable? And that would be the one on top because it's secondary, and the one on bottom is primary. So the reaction does not happen like this, or I should say it does not happen as fast. So the reaction adding the hydrogen to carbon 1 to make the secondary carbocation is going to be faster, so that's going to lead to the major product. And then you have, so if we're reacting with HCl, then H plus and Cl minus, because it's a strong acid, right? So then the next step would be the Cl minus reacts. So take a lone pair on chlorine and make a bond to that carbon with the carbocation. So that would be your major product. The bottom pathway can happen. It's just not as favorable, it's not as fast. So that would lead to your minor product. Okay, so this reaction follows what's known as Markovnikov addition. So that means the hydrogen, or the electrophile, adds to the carbon of the double bond. That is the least substituted, so that is the carbon that has the most number of hydrogens. So in this reaction, for example, right, this carbon has 2 hydrogens, this carbon has 1 hydrogen, this has 3 hydrogens, but that doesn't matter because that's not part of the double bond, right? It's only the 2 carbons in the double bond that matter. So Markovnikov addition says add the hydrogen to the carbon with the most number of hydrogens, so that would be carbon number 1. And then you add the nucleophile to the carbon with the least number of hydrogens. So that would be one way that we characterize a lot of the reactions in this chapter, whether they follow Markovnikov or anti-Markovnikov addition. So further, this reaction is said to be regioselective because these two are what would be known as regioisomers, and it prefers one over the other, so it's selective in that sense. And so you should note that a carbocation intermediate is formed, right? That's the first step in the mechanism, is you make a carbocation. And so what does that mean? If you remember, every single time you make a carbocation, what do you have to do? Is you have to watch out for rearrangement. And so this next problem will illustrate that. So if you take an alkene with, could be HCl, could be HBr, typically not HF, because HF is just a very dangerous compound, so most chemists prefer not to work with HF. Okay, so if we step through the mechanism for this reaction, so we're going to take the 2 electrons in the pi bond, we're going to make a bond of hydrogen, and then you have Br minus. So now you have carbocation there, and now the first carbon is a CH3 because it picked up a hydrogen. So let me sketch this hydrogen out because we need it, because that's a secondary carbocation, and if we're working the mechanism, you need to sketch out the bonds so that you can see the electrons moving. So now this is going to do a 1,2 hydride shift. And this hydrogen is going to move to that carbon, take its 2 electrons with it. So now that's a CH2. And now that carbon's electron deficient, so that's where the carbocation is. And then in the next step, the Br minus adds. So take a lone pair on bromine, make a bond to that carbon. And then that would be your major product. So this is what's known as an addition reaction. Well, so obviously what you did is you added HBr, you added H there, and you added bromine. Ultimately, you ended up adding it there because of the carbocation rearrangement. Is it syn or anti? Well, it's both. So in this case, it doesn't matter which carbon you add it to because neither carbon has any hydrogens. They both have the same number of hydrogens, so Markovnikov's rule doesn't apply. But just wanted to use this to illustrate that. So you could add the hydrogen to the top or the bottom, doesn't matter. But then you get a carbocation on this carbon. And if you remember, carbocations are flat. So now there's a p orbital there. And, sorry, that should have been hydrogen that we added first. Oh no, that's right, that's a methyl group. So carbocations are flat, that means the Cl- could come in from the top, or the Cl- could come in from the bottom. So you end up getting both cis and anti-addition. The Cl could add to the same side as the hydrogen if it comes in from the bottom, or if it comes in from the top, it would have added to the opposite side. So you could have made that, and you could have made this. Sorry, this should be hydrogen. And that should be methyl. So you could have added the hydrogen opposite of each other, like here, or you could have added the hydrogen and the Cl opposite, or the hydrogen and the Cl to the same side. And then, of course, so you made 2 chiral carbons, so you would get all 4 stereoisomers because you could get the enantiomers of these as well. And that's because in the first step, so I added the hydrogen to the bottom, but I could have added the hydrogen to the top. And so that would flip the stereochemistry at the top carbon. And then the chlorine could have came in from the top or the bottom, so that would lead to all 4 stereoisomers. Okay, so for these last two, let's just predict the major product. So let's not worry about stereochemistry here, but you want to recognize that you get all possible stereoisomers when you add HCl or HBr. So for this problem, let's just figure out where does the hydrogen and carbon go, or where does the hydrogen and the bromine go, or where does the hydrogen and the chlorine go. So if this is carbon, I'll call that carbon A and carbon B. So you want to recognize you're just going to add H and Br across the double bond. But is it Markovnikov or anti-Markovnikov? So where does the hydrogen go? So hydrogen, or carbon A has 1 hydrogen, carbon B has 0 hydrogens. This follows Markovnikov's rules, which says put the hydrogen on the carbon that has the most number of hydrogens. So hydrogen is going to go to A. So if we were sketching the mechanism, we would take the double bond and make a bond to the hydrogen, and Br- would come off. That would give you the carbocation there, and then Br- would add to that carbon. And you get that. That's the major product. And of course, stereochemistry here is irrelevant because there's no chiral carbons in the molecule anyway. And for this one, so if this is carbon A and this is carbon B, A has 1 hydrogen, B has 0 hydrogens. So Markovnikov's rule says put the hydrogen on A and put the chlorine on B. So you would get that as the product, right? Put the hydrogen on A, so that becomes a CH2, and put the chlorine on B. Okay, so next reaction. So take an alkene with HBr and H2O2. So so it becomes helpful in organic chemistry if you just learn to recognize reagents. So you memorize reagents, and you just know what it's going to do to the reaction. So if you add HBr and H2O2, what that's going to do is add H and Br across the double bond, and it's going to do so in an anti-Markovnikov reaction, so opposite. So if it's anti-Markovnikov, hydrogen is going to add to the carbon of the double bond that has the least number of hydrogens, or the one that's more substituted that's equivalent. So if this is, I'll call that carbon A, carbon B, this has 1 hydrogen, this has 2 hydrogens. So Markovnikov's rule would say put the hydrogen on A and the bromine on B, but this is anti-Markovnikov. So you're going to put the hydrogen on B and the bromine on A. So the product would be that, right? So we put the hydrogen here. Or let's say this. So we're going to put the hydrogen here, and we're going to put the bromine on A. And then that would be your major product. So why does this happen that way? So you just have to know the mechanism. If you know the mechanism, then that allows you to understand why reactions happen the way they happen. So what happens in this case is the peroxide oxygen-oxygen bond is weak, so that will break apart to make two hydroxyl radicals. And then the hydroxyl radical will react with HBr, so it'll abstract off a bromine or hydrogen atom to make a water molecule and a bromine radical. And then the bromine radical reacts with the alkene. So we could add the bromine to A or B. So let's consider both possibilities. So we're going to split the double bond and use one electron to make a bond to bromine. So now it's free radical, so I'm using single-headed arrows. And the other radical would, or electron would stay behind on carbon B. So if we added bromine to A, that's what you would get for the carbon radical. If we added it to B, so take two electrons to make a double bond, and the other electron stays behind on carbon. If we added it to B, you would get that. So which radical is more stable? Well, this is secondary. This is primary. So secondary is more stable, so that's not the preferred pathway. The top one is the preferred pathway. So you just added the bromine to the least substituted carbon, and that's going to force the hydrogen to go to the other carbon. So that is an anti-Markovnikov addition, and it's anti-Markovnikov because of that step right there. That determined whether this reaction was going to be Markovnikov or anti-Markovnikov. Okay, so what happens in the next step is that radical you just made pulls off a hydrogen atom from HBr, and now you have the major organic product. So you showed how the product is formed, so now it's a free radical mechanism. You can show the termination steps. So there were three different radicals in this mechanism, right? We had a radical there, we had a radical there, and we had a radical there that are all three different. So termination steps, any combination of those three radicals. So that leads to 6 possible termination steps. Right? You could remake peroxide, or the hydroxyl radical could react with HBr, or the hydroxyl radical could react with the alkyl radical. And you can make a little bit of that molecule, but all of these are happening in very minor amounts. So you don't make a substantial amount of any of these. It's just illustrating how this reaction shuts itself down. You could have made a little bit of that, or you could have made a little bit of this. Would be the possible termination steps. Okay, so you do need to know the mechanisms for these reactions, but more importantly, well, I shouldn't say that. You should just know them all. Just know how to predict the products and know the mechanisms for the reactions. But it's useful to not have to think about the mechanism every single time you want to predict a product if you just know what the reaction is ultimately going to do. So in this case, it's going to add H and Br across the double bond. It's going to be anti-Markovnikov. So where does the hydrogen go? This has 1 hydrogen. This has 0 hydrogens. If it's anti-Markovnikov, hydrogen goes to the carbon with the least number of hydrogens, so that is A. And bromine goes to the carbon with the most number of hydrogens, so that is B. So that would be your major product. And so this only works for HBr, not HCl, not HI. Okay, so if we just summarize what we've covered so far, so we've looked at 3 different reactions. If it's H2 in a metal catalyst, you add hydrogen and hydrogen across the double bond. It's neither Markovnikov or anti-Markovnikov since you're adding the same thing. It's a syn addition, so you have to illustrate the stereochemistry that the 2 hydrogens add to the same side. There's no carbocation, so you don't have to worry about rearrangement. If it's HX, HCl, HBr, you add H and Cl, or H and Br. It's Markovnikov, so hydrogen goes to the carbon with the most number of hydrogens. You get both syn and anti addition, and you do have to worry about carbocation rearrangement. If it's HBr, H2O2, you add H and Br across the double bond. It's anti-Markovnikov. We didn't go over the stereochemistry, but it's both. You get all possible stereoisomers. And there's no carbocation, so you don't have to worry about rearrangement. Okay, so let's look at 3 more reactions in this lecture. So this will be the hydration of alkenes. So that would be adding water across the double bond. So you're going to add H and OH across the double bond in this case. So if we did this reaction with, so this would be your recipe, water and sulfuric acid. So if you did this reaction, then what your product would be that. Or let's sketch it like this so that you can see. So we added H and OH across the double bond. So was that Markovnikov or anti-Markovnikov? Well, hydrogen went to that carbon which has 2 hydrogens, and OH went to the one which has 1 hydrogen. So you put the hydrogen on the carbon with the most number of hydrogens, so that's a Markovnikov addition. And if you did this reagent, then you get the same product here. So that's another way to do Markovnikov addition of water. So we'll talk about this reaction in a little bit more detail in just a minute. And if you did BH3 followed by peroxide and hydroxide, so the 1 and 2 means you do those reactions in sequence. You do the first reaction, and then after that reaction is done, then you add the next reagent to the same flask. So if you did this reaction, then your product is that. So we added H and OH again, but this will be anti-Markovnikov. Since we put the hydrogen on the carbon with the least number of hydrogens and the OH on the other carbon. Okay, so 3 ways to add water. 2 of them are Markovnikov and 1 of them is anti-Markovnikov. So if we look at the mechanism for these 3 reactions, so sulfuric acid is a strong acid. What do acids do is they donate, H plus, right? That's the definition of a Bronsted-Lowry acid, donates hydrogen. So those hydrogens are very acidic. So sometimes organic chemists, when they see H2SO4, they just pretend like it's H plus. So if you add H plus to this alkene, so hydrogen adds to the carbon with the most number of hydrogens. So that would become a CH3, and that would become a carbocation. And then water attacks. So I'll take a lone pair on oxygen, make a bond to that carbon. And then in the last step, you lose a hydrogen. So H plus comes back off of this molecule, off of the water that you just added. And so there's your major organic product. And you got H plus back. So you used an H plus to start, and you got an H plus back at the end. So that means the H plus is not used up. That means the sulfuric acid is not used up. So if something is useful to get a reaction going, but it's not consumed in the process, that makes H2SO4 just a catalyst. So you don't need much of it. You just need a drop or so of the sulfuric acid just to provide the H plus to get this reaction going. Although sometimes you might use more, but in theory, if it's just a catalyst, you don't necessarily need a lot of it. So the reaction is reversible. So as we'll see in chapter 10, if you take an alcohol with H2SO4, that can cause water to illuminate from the molecule and get the alkene back. And so if you wanted to favor the forward reaction, so you could just apply the Chartiers Principle, which we talked about in general chemistry too. So if you wanted to shift the equilibrium to the right, you could do that by adding more reagent, so add more water, and that would shift the reaction to the right. Or you could do that by removing products. So as the alcohol is formed, you could try to distill it, for example. And then if you remove product, then that would shift reaction to the right. Or if you wanted to favor the reverse reaction and take an alcohol and dehydrate it to lose water to make an alkene, then again, by Chartiers Principle, if you wanted the reaction to shift left, you could add more product. Or you could try to remove the water as it's formed, and then that would shift the equilibrium back to the left. Okay, so the other two reactions to add water. So this is what's known as mercury acetate. So OAC is acetate, if you remember what acetate is. Oh boy, how do I get rid of this? There we go. So this is what acetate looks like. So organic chemistry can get a little bit exotic. So a mercury with two acetates attached. So, and water is your first step. So what happens in this mechanism is we take the pi electrons and make a bond to mercury, and then that kicks one of the acetates off. So now mercury is attached to one of the carbons, but mercury's got unpaired electrons, which can be used to make a partial bond to the other carbon. So you don't have a true carbocation, which means there's no rearrangement possible since it's not a true carbocation. And then the next step in the mechanism, a water molecule adds to that carbon, and then you open up that three-membered ring with the mercury. So now you have this, and then you lose a hydrogen from the oxygen. And so then this would be what's setting in that flask after the first step in the mechanism. And then it's waiting for you to do the next step in the reaction to add the NaBH4. So NaBH4 is what's known as sodium borohydride. Anytime you see that, it's basically just a source of H-. So what happens in this step is one of these hydrogens comes off, takes the two electrons with it, and adds to that carbon, and then that kicks off the mercury. And so now then that's your major product. So now you've added hydrogen to the carbon with the most number of hydrogens, and the OH to the other carbon. So you did a Markovnikov addition of H and OH, but there's no true carbocation, so there's no rearrangement possible in this reaction. So that would be the benefit to do in this reaction as opposed to this reaction. If you wanted to add H and OH, but you did not want to rearrangement to happen, then you cannot use water and sulfuric acid if the carbocation was susceptible to rearrangement. This one is not, but maybe the alkene could lead to a carbocation that could rearrange, and if you wanted to avoid that, then you would have to use this recipe instead to add water. Okay, and then the third way to add water across a double bond is what's known as hydroboration oxidation. So that's the hydroboration step, and that's the oxidation step. Okay, so the way that this reaction works. So it's a pretty long, complicated mechanism. So we're going to take two electrons, make a bond to boron, and then the hydrogen from boron is going to add to that carbon, both at the same time. So this is a syn addition. And so ultimately, we're going to add H and OH syn to each other in the product because of that first step. Okay, so now we have an alkyl boron compound, and we still have two BH bonds, so this happens two more times. So now we can take another alkene and add to boron, take those two electrons in the pi system, add to boron, and then the hydrogen moves to that carbon. And now we have this molecule. And then we still have a BH bond, so we can do that again. We can take the 2 electrons in the pi bond, add the boron, and those 2 electrons go there. So the hydrogen moves there, and now we've got 3 alkyl groups bonded to boron, where the boron added to the carbon with the most number of hydrogens, and the hydrogen added to the carbon with the least number of hydrogens. So this step right here is making this an anti-Markovnikov addition, because hydrogen is going to the carbon with the least number of hydrogens. Okay, so we're not done, but that's what you get after the first step, is you add 3 of the alkenes to boron. And so now the oxidation steps. So hydroxide is a base, deprotonates peroxide to give this. And that peroxide conjugate base then adds to boron to give this compound. And then now what happens is a migration. So you get a 1,2 alkyl group shift. So the alkyl group migrates from boron to oxygen, and then hydroxide leaves. And that would give you this. And then that happens 2 more times because you got 2 more alkyl groups on boron. So another peroxide attacks to give you this, and then another migration happens. So another alkyl group migrates, lose another hydroxide, and now you have this. And then repeat that again. Another peroxide attacks. Now you have that, and then the 3rd alkyl group migrates, and another hydroxide leaves, and now you have this. Okay, so now what happens? So hydroxide attacks, kicks off this, and then repeat that process again. So another hydroxide attacks, right, kick off this, and now you have that, and then repeat again, another hydroxide attacks, and then you kick off that. And now you have 3 of these that have left, and you have boric acid. And then the alcohol, so the solvent here is water, so the conjugate base of the alcohol can pick up proton from water, and that can happen 3 times for each of these. And so then ultimately you end up with 3 molecules of the alcohol coming off of this. And the boric acid is a side product in the reaction. So that's a pretty complicated mechanism. So you want to know the mechanism, but you also just want to be able to look at this and know, okay, BH3, H2O2, that's just going to add H and OH across a double bond. And it's going to do so anti-Markovnikov. So you're going to put the hydrogen here, and you're going to put the OH here, and that's your product. Okay, so if we just summarize the 6 reactions we've covered so far. So for these last 3, right, H2O, H2SO4 adds H and OH across the double bond, Markovnikov. You get both all possible stereoisomers. There's a carbocation, so you have to watch out for rearrangement. If you do this recipe, again, that just adds H and H, Markovnikov, all possible stereoisomers, but there's no rearrangement. No carbocations, no rearrangement. And then hydroboration oxidation, add H and OH, anti-Markovnikov. It's a syn addition. The H, OH add to the same side as each other. No carbocation, no rearrangement. So we've looked at 2 anti-Markovnikov reactions. It's easy to remember them because you see that they both have peroxide in them. And those are the ones that are anti-Markovnikov. It's just a way to remember the reaction, which ones are anti-Markovnikov. Okay, so lastly, let's just predict these 5 products so that you can apply what we just covered. Okay, so this is just going to add H and OH, Markovnikov. So that would put the hydrogen here, and then you would get a carbocation here. and this carbocation is going to rearrange. So then your major product would be, so then you ended up putting the hydrogen here, and you end up putting the OH here because of the carbocation rearrangement. Whereas if you did this recipe, there's no rearrangement possible. So then you would put the hydrogen here, and you would put the OH there, because there's no rearrangement possible, but it is still Markovnikov addition. And if you did this, this will just be H and OH again, but anti-Markovnikov. So then the H would go here, and the OH would go there, because this carbon has one hydrogen, and this carbon has two hydrogens. So anti-Markovnikov, put the hydrogen on the carbon that has the least number of hydrogens. So you would make that as the product. Okay, and I put these two on. So this one just to illustrate the syn addition for this hydroboration oxidation. So A and B, this has one hydrogen, this has 0 hydrogens. So anti-Markovnikov rule says put the hydrogen on A and the OH on B. But it's a syn addition, so the H and OH that you add to each other have to be syn to each other. So they could both be on bottom. Or they could both be on top. And what's the relationship between those two molecules? They are in enantiomers. So 2 carbocarbons, so there's 4 possible stereoisomers, but you don't get the other 2 stereoisomers. The other 2 stereoisomers would be if you added the H and the OH trans to each other. Okay, and then this one is Markovnikov, so that's going to put the hydrogen on B, and that's going to put the OH on A, and that would be your major product. Okay, so that's 6 of the 15 or so, 20 reactions that we'll cover in this chapter. So I'll cover some more reactions in the next few lectures.